So in this section we will deep dive into Booth's algorithm. So until now we have seen how to get complement, the number systems, and how to do fixed point representation, how to do floating point representation. From this video onwards we will see about Booth's algorithm. So in this section two parts are important. One is division and another one is Booth's algorithm. So let's see. So Booth's algorithm do nothing but the multiplication part. Okay, so if I write what is 5 into 2, we can easily say that is it is nothing but 10, but it is doing it into decimal part. But we doesn't do the calculation of multiplication in decimal, because in processor everything is processed into binary code. So we have to convert it into binary, and then we have to perform both algorithm, then we can get these answers. So first prerequisite we have to understand that is basic, like it is in basic maths that positive into positive is positive, negative into positive is negative, and negative into negative is positive. So we have to understand that in fixed point representation we have seen how to represent a negative number. To represent any negative number we have to do 2's complement. Okay, these two things you have to remember out of the box. So when we will do minus into plus multiplication, we will get the answer negative, and the answer we got from the Booth's algorithm, we just have to perform 2's complement in it, and then we can get the actual answer we want. But in first and third case, we don't have to do any complement. The answer we get from the Booth's complement is our answer only. So I hope it is clear. Let's move on to the next section. So in this section, we will see the flowchart of Booth's algorithm. It will may come and it will come with a numerical too. So we will solve a numerical too, but let's first see the algorithm, what it says. So first it starts. So there are some terms you have to understand. That is, first is AC, there is accumulator, that is Q, and down there is -1. So I written it's like it's not Q minus, it's not that, it's like Q, down there it's -1. So Q -1 equals to 0. Okay, so you have to remember these two initialization, that AC is 0 and Q -1 is 0. M is called multiplicand and Q is called multiplier. You don't have to understand that. If we are doing 3 into 7 into 3, then 7 is called M and it is called Q. How to remember? Just remember that M alphabetically M come before and Q come after that. So the first thing is called M and the second thing is called Q. Okay, so Q is multiplier and M is multiplicand. Okay, so then there is count. Count is n. What is n? How many bits of register we are given. Like we have to solve in like 4 bit, 5 bits. Then the number of bit is given, that should be the number of count or n. Okay. By default, if nothing is given, we assume that n is 4, because majority of the question it will be like 4 or 5, but for safe side we generally consider it to be 4 if question doesn't mention it, that how many bits are given. So I hope you understand this point. That is, here we are doing initialization, that m is multiplying, q is multiplier, count is n, and it's done. You don't have to write this 4 bit in the flowchart, just exclude that, other thing will be same. So at first see the flowchart completely first. Yes, so I hope you see it. So let me explain it further on. So this part is done, so then the next part comes. So it is not multiply sign, it's more like comma, you can consider. It is q naught, q0 and q minus 1. So what is q naught, what is q minus 1, we will see, and you will understand the flowchart better when we do the problem again. But let me clarify the flowchart. So it is a condition statement type that it checks the condition, that is q and q minus 1. If the q and q minus 1 came to be 1 0 or 0 1, what it will do, it will, if it came to be 1 0, it will do AC minus m. Okay, how it will do, we will see. And then there is step is written, that is ASR. Okay, and it will return ACQQ1 and count equals to count minus 1. So if it come to be like 1001 or 0011, that is only the 4 combination it can give. So if it is done, we will do ASR. What is ASR? It is arithmetic static rendering. Okay, so I guess it is the name. I will tell you on the further on. Don't worry about it. It's like arithmetic static. It is something like that. ASR. Arithmetic shifting something. So let's assume that is ASR. I will attach it into the video itself. So don't worry. And then there is like AC Q naught. I mean Q naught or Q. You can assume Q, that it will give Q and q minus 1, then count will be subtracted by 1, and how much time it will go until the count is 0. Okay, so let's see the problem itself, then we will understand better. So what is ASR? Let me understand the ASR first, then we will just jump on to the problem statement, then we will see and understand the flowchart in a better way. So there is ASR. So let's suppose there is a number 1100. So how do we perform ASR? Arithmetic shift something. Arithmetic shift rendering maybe. So arithmetic shift rendering maybe. So let's recheck in Google. You will get that in Boost algorithm. So understand the process. That is, we have to shift it. We have to discard the last value. In my case, the last value is 0, so I am just discarding it and moving forward every digit, and the first digit is repeated. So let's suppose there is like 1000. So how to perform ASR? We have to first discard the last one. So last one is discarded and move forward every digit, and the first digit is being repeated. So let's do this. 0 0, there is 1 1. So 1100 we got as ASR. So I hope you understand it. So what it will do, and it will make sense when we solve a problem in it. So let's solve a problem. So here it comes, that by Booth's algorithm solve 7 into 3. So first step we have to do is, first we have to convert the decimal numbers, that is 7 and 3, to binary codes. Okay, why we are doing like 4-bit format? Because no bits are recommended or given. If it is given as 0, then we just have to add a 0 previously, like represent 7 as 5-bit, we have to do 0 0 1 1 1. Okay, so here we are converting it. 1 1 1 is like 7, and if there is 6-bit, we have to 0 before 0. So if before zeros are given, so it has no value, so we can add zeros. So it is in 3-bit, but as I know that every time to solve this type of problem, we have to make it in 4-bit if the bits are not given. So here it is not given as 4-bit, so we have to do it like 4-bit. So we are doing it in 4 bits. So yep. And for q, it is like 3 3 is given in decimal numbers, we are converting it to the binary. So you got that. So first step is this. So as we have seen that in a step we have to do AC equals to AC minus M. So AC is also in binary, M is also in binary, and as we know that making the subtraction is like, subtraction has some bit odd rule. It good is like 1 minus 0 0 minus 1, but from 0 minus 1 it's getting complicated. So what we can do, we can write like AC equals to AC plus minus M. Okay, so if uh, plus is multiplied by minus, then we will get minus, so it's the same. So to avoid subtraction, what will we can do, that is AC minus AC plus minus M. Okay, so what is M here, what is Q here? So first digit is M, so M is 7, and another one is 3, so that is 3. And here we are doing minus M, so where we need the AC minus M, we can just replace it, that we can add, because addition is generally easy in binary. Okay, that's why you can do minus also, but minus is bit tricky for me. That's why I'm using this approach. I should recommend that you should do the same approach too, because it is easy. So AC minus M. So what is M here? So M is nothing but 001. So how we can do that, is minus M means minus 7. So how we can represent minus 7 into binary code, that is we have to do first complement. So first complement of this number is like we have to replace all ones with 0, so 1000, then we have to add 1, so that is 1001. So you got the minus M part, that is 1001 in binary format. So yep, so it is like step 1 only. Then there is like 4-bit representation, so we have to do 4 cycles. What I mean by cycles, we will understand in few minutes. So let's start. So it is a thumb rule that how many bits are given, that many cycles it will be gone. Like if there is 5 bits, it will run like 5 cycles. If 6, and you got this. So then the chart has to be made. How the chart has to be made? There should be first accumulator, I mean AC, then there is Q minus 1, and there is operation. You will write in full format, I am writing in like short format. Okay, first thing. Second thing is AC, Q, both are in 4-bit format, only Q minus 1 in 1-bit format. Okay, remember these things. These are small things, but it will be easy for you to go with it. If there is 5-bit, it will change, but Q minus 1 is always in 1-bit format. Okay, so let's see what is cycle, I mean how cycle is being done. So as we have seen in the flowchart, so here is the flowchart. In the initial section, in the first step, what is saying in flowchart section, the first section said that AC is 0, Q minus 1 is 0. Okay, so first we have to write AC is 0, so it is 0 in 4-bit format, Q minus 1 is 0 in 1-bit format. Then Q is given, that is 0001, so we are writing that Q0001. Okay, so then we have to perform some operation. So what operation we need to perform, and how we will determine that it is performed. So what is Q0 in the flowchart? The Q0 is this, the last term of Q, I mean the first term of Q, that is first term, that is 1. So the last one is the Q0. Here what is the last term? 1. What is the last term here? 1. So Q0 is 1. What is the last term here? 0. So Q0 is 0 here. Okay, you got this. You are getting this. So if there is 1 and 0, if there is 1 and 0, what we have will what that is 0 1. So if there is 0 1 in flowchart, what it says, if Q1 and there is like Q0 and Q1, and we are getting 0 and 1, like Q0 is 0, so here we can see clearly wait, okay, that's my fault, I guess. Q0 is 1. No, that's not a fault, because like wait a bit, let it focus. So Q naught is 0, and Q naught is 1, and Q minus 1 is 0, so that is